Assalamualaikum and very good morning all. So we now go to the next part of CE, which is the modes of operation in capillary electrophoresis. We have several modes. That's what making a CE a universal analysis and detection system, because it contains a lot of modes that can enable separation depending on your application. Okay, I outline here the most commonly used in CE towards the one that is specialized into certain analyte. Okay, the most common one is, of course, the first one, capillary zone electrophoresis. This is only for charge analytes. Okay, this is in line with the initial principle of CE. Okay, negatively charged or positively charged. And then from the first mode, researchers find out how we can analyze neutral, because we also have analytes from neutral sites, right? So it come out with micellar electrokinetic chromatography, MEKC, second mode of operation in CE. This is introduced in 1984. This is only like 36 years old. Okay, and this is the breakthrough for neutral separation in CE. From the name itself, you can see that chromatography is here. Why chromatography is here, I will explain to you later, but this is still in CE instrument. And then we have capillary gel electrophoresis. So this is like the initial CE breakthrough around 50 or 60 years ago, whereby this capillary gel electrophoresis is literally using gel to separate DNA or proteins. Okay, so this is DNA and proteins. Okay, and then we have capillary electrochromatography. Again, the name itself, chromatography. And then we have capillary isoelectric focusing and capillary isotachophoresis. These two methods are what we call as online pre-con method in CE. Means that apart from analysis, we can also concentrate the analyte from very dilute towards very concentrated, so that detector can see the analyte better. Okay, all this while we can only do that using extraction, right? But in CE we can do that as well. Okay, let us go on the first one first. So this video will be talking about this 1 and 2. Okay, and then the next video will be talking about 3, 4, 5, and 6. Okay, so capillary zone electrophoresis, from the name itself, zone, means that the separation is based on zone. Imagine in a capillary CD detector, okay, when you inject analyte here, when you inject here, you are injecting a solution, right, containing several analytes. Okay, and then when the electric field is there, okay, components inside this solution will start to go towards detector depending on the charge. Okay, and they move toward detector based on zones. Okay, 1, 2, 3, okay, 4, for example. Okay, if you see from the zone size, it is in contrast with what we have in HPLC. Okay, in HPLC, I showed you before that the analyte, if we have the same 4 analyte, they are moving like a bullet. Okay, why? Because we have all those laminar flow, diffusional, everything, right? So that's why you have a peak like this, a bit broad. Okay, in CE, in the other way around, we have very efficient peak, because it is moving like zones. That is the meaning why we call of zone electrophoresis. It is moving depending on its own zone. Okay, for example, this is positive, this is two positive, and then this is positive depending on different charge, and also mass. So it is moving because of the zone. in order to separate based on zone, okay, the analyte must have difference in the charge and ionic radius. Means that it is only applicable for charge sample, right? Nothing to do with neutral. Cannot do neutral. Okay. How to do this? Okay, we fill the capillary with the buffer and introduce by injecting it here, and then just apply electric field. That's all. Okay. So this is how the zone looks like. Okay. So first is if let's say this is negative, first is going to be positive. Why neutral is also here? Neutral will also move towards detector because of the EOF pump, remember? But it will not be separated well if it's together with several other neutral. If let's say you have 3 neutral, means that this one peak will only will represent all 3 neutrals. Okay, they cannot be separated. So this the first zone will meet detector first, therefore in electrophoregram it will be the first, and the third zone will be the last, therefore in the electrophoregram it will be the last. Okay, the other way around, okay. So in detail, CZE, okay, the small and highly charged ion move fast. Okay, we discussed this before. And the one that is having a higher mass and low charge, for example, if it's only having one charge, it will move slower. Means that in the previous slide, this one is the third zone, this one is the first zone. Okay, the other way around, if you have the opposite charge lah. If let's say first you have a positive, negative, of course positive will go first. If you have negative, positive, for the polarity, negative will be migrated first. Okay, the other way around. Okay, this is also moving by EOF. We discussed this before. Okay, here the EOF is moving faster than electrophoretic mobility depending on the buffer strength. EOF will always move from positive to negative. Okay, EOF flow will always move from positive to negative. Okay, if you analyze negatively charged analyte using positive polarity, of course negatively charged want to go here, right? But do we want negative to be here? No, because the detector is here. So who's going to push this negative towards the detector? Is going to be the EOF. EOF will push all this negative towards detector because EOF is functioning as a pump. Okay, that's why for neutral analytes, EOF will also push it to the detector, but neutral will never be separated in CZE. Okay, what if you have neutral analytes? Okay, later we will discuss about MEKC. Okay, so this is the example of the anionic separation in CZE. Okay, how do I know this is anionic? Because all those compounds are all negatively charged. Okay, so in this case, fluorine is the last one to migrate. Find out in your periodic table why fluorine is the last one. Okay, it must be something to do with the mass. Okay, so this is the buffer phosphoric acid. So this is another example of the determination of anions and cations. By the way, by default, in a single separation, if you are using positive, negative, it can separate both. Okay, both because of the existence of the EOF. Okay, of course positive will be detected first. Okay, why? Because the electrophoretic mobility will make positive go on its own, but how about negative? EOF will push negative to this one. So in this case we have both separation in one go. Okay, now what if you have neutral compounds to be separated in CE and you only have CE instrument to do the work? Okay, you don't have any HPLC, you don't have GC, whatever lah, you don't have, and you only have CE. But you know CE is only for charged compound. So in order to do this, you add micelle. Okay, you all know micelle, right? It's coming from the surfactant. So micelle, one of the example of micelle is sodium dodecyl sulfate, which is also a surfactant. Surfactant you are commonly used in your daily toiletries, okay, or even your dishwash detergent. Okay, so this micelle is like the tadpole, head and then tail. Okay, so this tail over here is the long chain of hydrocarbon. Means that is very non-polar lah. While the head over here is very hydrophilic. Why? Because it's containing charge substituent. Okay, this makes surfactant when prepared in certain concentration forming micelle. So this is the whole thing we call it micelle. Okay, this micelle will help your neutral to be separated in CE by means of complexing. Okay, the keyword is complexing. Why complexing? It's like your micelles, like millions of them, will trap your neutral analyte inside here kan. Neutral usually apa, anthracene, all those naphthalene, they are all non-polar organic molecule. So they will be trapped at the tail end of this micelle. When it is trapped, all those charges, see, negative ni, will be seen in CE as a charged compound. Means that when it is complexed by micelle ni yang akan bring the neutral inside here towards detector. That is what we call as like assisted migration. The micelle is assisting the separation of the neutral. And because we have the micelle inside the system, inside the capillary, maksudnya kita inject micelle, that's why we call it chromatography. Because remember, what is the first principle of chromatography? For us to call it chromatography, if it is having stationary phase and mobile phase. So in this case, micelle is acting like a pseudo stationary phase. Why we call it as pseudo? Because the stationary phase will only be there if we introduce them. Okay, how do we introduce them? Is by injecting the micelle lah. If we take out the micelle, then there's no separation. Stationary phase. So that's why we call it pseudo. Pseudo ni macam ada tak ada lah. Means that kejap ada, kejap tak ada. Okay lah, depending on the application. So that's why the name it is called as chromatography. But this is not to be confused with liquid chromatography. So and then the name ada micellar. Another one is electrokinetic. Why? Because it is moving also using electric field. Tak ada electric field, no point lah. Okay, so the one that I show is the negatively charged head. Because we are using the anionic surfactant. Yeah, anionic surfactant. But what if you want to analyze with cationic micelle? So we also have a cationic micelle, what we call as CTAP. CTAP ni cetyl triammonium borate, I think. No. Okay, you have to find out what's inside Google. Okay, because this is not commonly used. I always use SDS in my application. Okay. Okay, in order for you to make micelle, you have to prepare your surfactant according to the concentration. Okay, for example, SDS tadi tu, sodium dodecyl sulfate in the previous slide, it can be giving you millions of micelle if you prepare the SDS having concentration of 8.2 millimolar. Okay, sikit je. Means that you prepare only a bit, you can get micelle already. Okay, if you prepare like 80 millimolar, then this number is going to be higher lah. But in CE, the higher the concentration of each component, of course will increase apa? It will increase current. Okay, you learn in your physics, right? A lot of components inside solution will increase apa? So increase current lah. Means that the arus will move a lot lah. Okay. And then we have C-tag over here. Have you found out what is the full name of this? And then we have zwitter ionic surfactant. Zwitter ionic, I hope you know, is containing both positive and negative. Means that we can manipulate. If you want to use positive, you use prepare something lah. So this is more interesting because it contains both. We don't have to buy two things of surfactant in our lab. Okay, and then we also have non-ionic. Non-ionic also can help you depending on your application. So this is how exactly the separation looks like inside the detector. Okay, just now I said to you, anionic surfactant is the most common. Okay, but it is anionic, right? If you do positive polarity, means that you start from positive to negative. My cell of course want to go here, kan? Logic kan? Why logic? Because it's negatively charged. Negatively charged always want to go to positive. But how can we detect it here? Okay. Again, it is because of the EOF pump. Not pump per se lah. Pump, quote and quote. This EOF pump will be produced when you prepare your BGE. Okay, BGE more than pH 3, right? If you prepare your buffer more than pH 3, you can have the EOF. And later you will detect all my cell towards detector. Okay, you see this analyte inside the like framework. Okay. Okay. So in MEKC, it is not straightforward to calculate the resolution because of the existence of the micelle. So in order for you to calculate it, you can use this resolution. But fret not, I'm not going to ask you how to calculate resolution in MEKC lah, because this will take a lot of work to calculate. Usually in our lab, we just use the software to calculate it for us, or even the software from the instrument itself. So this is how electrophoregram of MEKC will looks like. Okay, if you are preparing, if you are doing MEKC in negative, positive mode, positive polarity, means that starting from positive to negative, who will come out first in detector? By the detector, EOF will be detected first. Why? Because EOF is the fastest among all. So what they pump? They pump. Of course, it will be there first. Okay, sometimes EOF will give you peak if you put an EOF marker. And then the next one is your analyte. Okay, analyte inside the micelle. And then the last one is the micelle only. Means that the remaining micelle lah. Okay, so this is how the elution profile for neutral solutes. Okay, my question is, can we use MEKC for charge analytes? Boleh tak? Can we use it for charge analytes? Okay, later we will discuss and we will see whether we can find anything from the reference. Okay, so this is MEKC of different kind of compounds, and they can be detected. So basically this electrophoregram actually is answering my previous question in previous slide. Okay, go into the internet and find out all this structure. Okay, I believe they are not neutral. some of them are neutral, some of them are charged, and we can get all analyzed. So it already answered my question just now, but how?